Welcome now to recording number 2 for chapter 9 of Larson, where we look at project crashing. In this video, we're going to look at crashing and the implications of what it actually means. There's a short video clip within it, and I've found that's a nice explanation. A good explanation of how crashing actually works. So I was quite impressed with it. So I've done that, but then also what I want you to do is to look through the exercise which is on in the textbook. Okay, crashing. Crashing, as you know, shortening a project. Here's a really nice video. This man taking you through the exercise in crashing this project.
Now I'm going to do the first crashing problem. Here we have a network, and we're interested in reducing the duration of this project, and we want to do it as cheaply as possible. So we're going to use the least cost method of crashing or reducing the duration of a project. So the first thing we need to do is figure out how long it would take normally and what the total direct cost would be. So we have the durations in the boxes. We're not interested in slack and forward and backward pass, so we're keeping things simple in terms of a single cell in terms of duration. And we look here, 1, 3, 3, and 3, that's 10, 1, 4, and 4, and 3, that is 12. So this is the critical path. And the normal time is 12. We total up the normal costs here, and that comes to 1,000. So now we're interested in seeing how much it would cost to reduce this network from 12 to 11. So here we want to look at the cost associated with crashing activities. And we have to look at these two columns. The first column, maximum crash time, tells us how many days, let's say, that we can take off for a given activity. In the second column, the crash cost, or the slope, is how much it costs us to crash that activity each day. So for activity A, we can't take any time off the normal time of 1, which makes sense, and doesn't cost anything. But activity B could be reduced all the way to 1 day in terms of time, and for each day would be $100, let's say. So if we're going to take it off from 3 to 2 would be 100, and from 3 all the way to 1 day it would be $200. Activity CD, we can take off 1 day, cost of 50 and 60. E is 2 days, $70 each, and 1 day for activity F at $90. So we look at the critical activities and pick the one with the cheapest crash cost. And we look at C, the cost is 50. We look at E, the cost is 70, and we look at F, the cost is 90. And we choose the cheaper cost, which would be C. So for $50 additional, we can go from 12 to 11 days. So let me move this up a little bit. Go ahead and record those changes. Put a 3 in here for C. We've crashed it the 1 day we can, so we put an X there. 3 up here. None of the other activities have changed. Put in 3. We indicate that we crashed activity C at a cost of 50. 50 plus the 1,000 gives us a total direct cost of 1,050. Now we want to see what it would take to get from 11 to 10. And here again we look and identify the critical path. 1, 3, 3, and 3 is 10. This is 11. This is still the critical path. Now 2 of our options aren't available, so we're looking at E or F. E costs 70, F costs 90. Choose the cheaper one, which happens to be E in this case. So I've gone ahead and recorded the change in E, taking it from 4 to 3, recorded it over here under activities changed, and added that to the 1050 to get 1,120 for the direct total cost for doing the project in 10 days. Now let's see what it would take to get it to 9. We check our critical paths. 1333 is 10. 1333 is 10. So now we've got 2 critical paths. And this is to be expected as we begin to compress that network and reduce slack as a result of that. So now we have to influence both paths. And we have 2 options available to us. We can crash E in some combination of B or D. E costs us 70. B costs us a big 100. D costs us 60. So the cheapest option there would be D and E, which would be 130. Or we could crash F, which is on both paths, and even though it costs 90,000, it would be cheaper than crashing 2 of the other activities. So we would choose F in this case. So we'll do that and show you the next sheet in a second. So I've gone ahead and recorded the change in F. The 90,000 has been added to the previous total to give us a total direct cost of 1,210 to do the project in 9 days. Notice I put an X next to in the F box because we used up the 1 day we could for that particular activity. Now let's see what it takes to get from 9 to 8. We know from our previous work that we have 2 critical paths. We killed 2 birds with 1 stone with F, but now we're going to have to reduce 2 activities in order to go from 9 to 8. We know we have to do E because that's the only way we can influence this path, given that the other 3 have reached their crash points. Now we have to choose between B or D, and B we know costs 100 and D costs 60. So we're going to have to add that with the cost of E, 60 and 70, to get us from 9 to 8. So I've gone ahead and recorded the changes in both D and E, put X's next to them because they reached their maximum crash time, total up the 2 costs. We got a new total of 1,340 to do the project in 8 days. Now let's see what we can do in terms of getting to 7. Check here. Still got our 2 critical paths. But notice that this path, A, C, E, and F, each one of these activities can't be crashed any further. They all have X's. And therefore, even though we could crash B, nothing would be gained from that in terms of shortening the duration of the project. Because even if B was done in 2 days, and therefore D was done at the end of the 5th day, F would still have to wait 6 days for E to be done. So now we've reached what's called the crash point for the network. The point where, given the information that we have, the nature of the network, what was possible in terms of crashing, we can reduce this network no further than 8 days. And again, the key point here is all the critical paths have to be able to be changed in order to shorten that duration. And in this case, one of the paths is X'd out. As soon as you see that, you know you've reached the crash point for the network.
So there we are. And I think that's a really nice illustration in real time of how the whole crash point and crashing project works. If you look in the text, there's a good example here. It's a worked example. It has the data set, as you can see here. You have the activities, the slope, that is, the costs, the maximum crash time, the normal time, the crash time, and you want to reduce it from well, 3 and 6 is 9, and 10 is 19, 30, 38, 38 and 5 is 43 and 6, 49 days. You want to reduce it to 2 and 4 is 6, and 9 is 15, and 7 is 23, 29, 33 and 6, 39 days. So basically what we do is we look to see how you move it. Your total time here is 25, and as you go through each one, you take some time out. Then you go down to 24 days, then you go down to 23 days, down to 22 days, down to 21 days. And basically what it's saying is, look, 21 days looks like your maximum crash point. There's sort of no more excess to be taken out. And then basically you start to do a summary of it, what the best point has been. And as we see here, this really looks to be the cheapest option. 22 days, 21 days, too much more. So basically, this is where you start looking at the optimum crash point at 22 days, beyond which your total project costs start to increasing. But that, of course, that decision would require a trade-off. You might say, well, we need to make it even shorter, but we're prepared to pay more. That's a management decision. So this is why you need to be certain of your decision-making processes, but also the cost estimates that you're using upon which you're then basing this exercise. So look, I really would recommend that you take your time, go through that exercise, try some of the worked examples. As you can see, it's fairly straightforward, but you need to be able to test all your assumptions on the way through. And what you do is you use the project cost duration graph, as we've just shown. You need to know crash times. So you need to know the details of all your work breakdown structures and all your activities, which means you need to go back and have a look at the cost of them. You make this assumption that there is linearity, that as one variable changes, dependent variables change as well. You know that from your statistics and looking at correlation, so that as you change one set of variables, others change, and they change within a known relationship. You keep going back and you keep saying, which other activities can we crash, until we reach the point at which you've got the optimum crash point. And you need to make some decisions then and do some sensitivity analysis around, if you reduce time and increase costs, what does that mean? Is that going to be a decision that we can't sustain? You know, we can't increase the project cost by 20% just to reduce its length by 10%, unless there are reasons which you do in your sensitivity analysis as to why you might do that. So why do we, if cost, not time, is the issue? So you've got to take some costs out. Well, you might want to do that because someone says, you know, the funding for the project has changed. When you think of the current environment, and it's the second semester 2020, we're in the midst of the COVID-19 pandemic. We know the economic indicators basically around the world are very fluid. Growth has stopped. Revenue for a lot of businesses has stopped. And as that revenue stops or drops, corporations and governments revise all their internal financial plans, and they may say, we have to save 10% of our outgoings, and we're doing that by looking at all the projects we're going, and each of our projects has to have its cost reduced by 10%. That's how these things happen. And they might say, well, we're happy to reduce the cost by 10%. What we'll simply do is we'll roll them over longer. So we're happy to make that trade-off between costs and quality. Or you might say to the owner of the project, say if you're undertaking a project for a business, you might say, and the business owner says, I want to do this now not in 15 days, I want to do it in 12. And you might say, well, we can do it in 12, but you need to do 3 days worth of work yourself. In other words, we basically give you more responsibility, make some more key decisions, or just shift the costs onto them. They may be happy to share the costs. You might decide to outsource the project or a significant component of it. Or better still, you might get all your team together, plus others, and say, let's brainstorm. What other ways are there of looking at this project and finding opportunities to reduce costs, reduce duration, reduce scope. Remember, it's about being open and flexible with your thinking and not being constrained. And this often gives you an outside perspective and allows you to do that, which of course makes project management quite exciting and interesting. So I hope you've enjoyed that chapter.